Listen to this chord. It's an A major chord played on a piano. To your ear, or to a microphone, the physical reality of this sound is surprisingly one-dimensional. It is just a single fluctuating measure of air pressure over time. If you were to play just one single pure note, the graph of that pressure versus time is a clean repeating sine wave. But when you play 3 notes at the same time, those 3 corresponding sine waves simply add together. At any given point in time, the height of the resulting wave is just the sum of the heights of the individual pure waves. The result is a much messier, more complicated wobble. Now, your ear has no problem hearing that messy wobble and breaking it back apart into the distinct original notes. But mathematically, given only this final squiggly line, how do you do it? How do you unbake the cake? How do you unmix the mixed wave to find the pure, hidden frequencies that created it? The mathematical machinery that accomplishes this seemingly impossible task is the Fourier transform. It is without a doubt one of the most important mathematical discoveries of all time. And to understand how it pulls this off, we need to change our perspective. So, how do we build a mathematical machine that can look at this messy wave and unmix it? The first step is to completely change our perspective. Instead of viewing this wave stretched out over time, let's take it and wrap it around a circle. Imagine a little vector pointing out from the origin. As we move forward in time, this vector rotates, and the height of our wave dictates the length of this vector. If the wave is high, the vector is long. If it's low, the vector is short. Right now, we're rotating this vector at a somewhat arbitrary speed. Let's call this speed the winding frequency. At half a cycle per second, the wrapped wave just looks like a tangled mess. But watch what happens as we smoothly increase this winding frequency. The wrapped shape morphs, spins, and tangles itself in beautiful ways. Most of the time, the peaks and valleys of the wave are distributed evenly around the circle. But notice this moment. Right when our winding frequency hits exactly 3 cycles per second, which happens to be one of the pure notes mixed into our original chord, something magical happens. All the peaks of that specific 3 Hz frequency line up on the right side of the circle, and the troughs line up on the left. The entire shape stops being a balanced tangle and drastically bulges out to one side. Just a fraction of a hertz later, it turns back into a balanced mess. This geometric bulge is the key to unlocking the Fourier transform. So, how do we capture this visual bulging mathematically? Imagine that this wrapped-up wire has a uniform mass. We can track its center of mass, which I'll mark here with a red dot. As we sweep through different winding frequencies, watch what happens to that dot. For most frequencies, the peaks and troughs of the wave cancel each other out, keeping the center of mass pinned right near the origin. But when the winding frequency exactly matches a frequency in our signal, the bulge pulls the center of mass significantly off-center. To describe this mathematical unwinding, we need a way to track continuous rotation in the 2D plane. Enter Euler's formula. As a quick refresher, the expression e to the I theta describes a point on the unit circle in the complex plane. If we make that angle proportional to time, writing e to the negative 2 pi I ft, it describes a point rotating continuously around that circle at a frequency f. The negative sign just ensures we are rotating clockwise by convention. To wrap our original signal, let's call it g of t. We just multiply it by this rotating complex number. The length of the rotating vector gets stretched and squished by the value of g of t, tracing out our wrapped shape. Now, how do we find the center of mass of this continuously rotating line? We sum up all the points along the curve and divide by the total number of points. In the continuous world of calculus, this sum becomes an integral. We integrate g of t times e to the negative 2 pi I ft over our time interval and divide by the time duration. And there you have it, the exact formula for the center of mass. The actual Fourier transform drops the division by time. It just scales the result but makes the math infinitely cleaner. What you are left with is an equation that outputs a single complex number. Its magnitude, the distance from the origin, tells you the amplitude, or how much of that frequency is in the signal, and its angle tells you the phase, which is the starting shift of that specific wave. To really see the power of this mathematical machinery, let's keep track of that center of mass as we change the winding frequency. We'll move our winding machine over to the left. On the right, let's draw a new graph. On the horizontal axis, we'll track our winding frequency, and on the vertical axis, we'll plot the distance of our center of mass from the origin. Watch closely what happens as we slowly crank up the winding frequency. For most frequencies, the wrapped shape is beautifully balanced around the origin. The center of mass sits exactly at 0, and our new graph just flatlines. These are the empty frequencies. They aren't part of our original sound. But right when the winding frequency matches one of the hidden frequencies from our original piano chord, the wrapped shape bulges. The center of mass drifts away from the origin, and our graph draws a sharp, prominent spike. As we continue to sweep through the frequencies, we get a spike for every pure note that was hiding in the mix. This new graph is what we call the frequency domain. We've taken our original tangled signal in the time domain and transformed it into a clear, distinct set of peaks. It tells us exactly what notes are playing and how loud they are. And the truly beautiful part? This process is completely reversible. If you take the pure sine waves represented by these specific spikes and simply add them back together, you perfectly reconstruct the original messy wave. Unspooling the frequency domain back into the time domain like this is known as the inverse Fourier transform. Zooming out, what we've just built is essentially a mathematical prism. The Fourier transform takes a messy, tangled signal that exists in the time domain and transforms it into a fundamentally different perspective, the frequency domain. It isolates the pure, unmixed ingredients of reality. And while we started with a piano chord, this exact geometric machinery is one of the most powerful and ubiquitous tools in all of applied mathematics. When your computer compresses a photo into a JPEG, it's essentially using a two-dimensional Fourier transform to find the underlying spatial frequencies of the pixels, keeping the big sweeping colors and throwing away the unnoticeable high-frequency noise. Electrical engineers use this exact same math to filter out interference from radio signals. It's even the foundational language of quantum mechanics. In fact, the famous Heisenberg uncertainty principle, the idea that a particle cannot have both a precise position and a precise momentum, is just a natural mathematical consequence of how a highly localized wave transforms into the frequency domain. It even makes impossible-looking differential equations suddenly solvable by turning calculus into simple algebra. The Fourier transform takes the chaotic reality we observe and reveals the pure, elegant symmetries hiding underneath. It is a perfect reminder of how a simple shift in perspective, just winding a line around a circle, can unlock the hidden structure of the universe.